I am going to be making a video about acceleration. And first of all, how I'll be doing it, I'll be dropping a softball in my brain. Whenever I say distance, or have it on labeled distance on a graph, it means total distance the ball has fallen. Time means the time since I dropped the softball. Speed means the speed of the ball. And I'm going to be ignoring things like air resistance. Oh, I probably spelled air resistance. Oh my god, I spelled air resistance terribly. I'm going to be ignoring things like air resistance and the ground. Now, for this video, I need 4 graphs. I need the speed and time graph. I need the speed and distance graph. I need the distance and time graph. And I need the time and distance graph. So, since the ball is falling, affected by gravity, this is what the speed and time graph looks like. That's just how gravity works. That's how acceleration and gravity work. It's a linear equation, y equals kx. What I was thinking about this, and I wasn't sure how to go about doing it. And so I eventually figured it out, and that's what this video is about. How can you figure out the speed if you know the distance? What does this graph look like? Is it like something like, does it go like up really quickly, or does it like sort of flatten out, or does it go like straight? Whatever. The point is, to make this graph, I thought, well, hold on. Speed and time are linear. So that means wherever I have speed, y, I can substitute it for kx. And since the k part depends on the axis labels, which I'm not using, I can basically just put speed wherever time is, and vice versa. So this then turns into this. Time distance, speed distance. So that is much easier. But, well, this actually isn't easy. I don't know if you would be able to figure this out just thinking about this. But luckily, this is easy to figure out because this is easy to figure out. This, obviously, just looks like this. Because, right? Because you're going faster and faster and faster, so that you're like going farther and farther and farther and farther. You know, that actually looks like a ball being dropped. So then, to get from this to this, we simply flip the axes, and it looks like this. Oh god, I should not be making YouTube videos. The point is, this graph is time and distance, which makes sense because if your distance is going up at a constant rate, time will be moving slower and slower relative to distance, which doesn't really make sense, but you know what I mean. So, then I'm going to go back, and then I remember how I said time and speed are basically interchangeable because it's a linear graph. So then I go back to, hold on, this graph, and since this graph is basically the same as this graph, I'll just draw it in, and that was the answer to my question. It looks like this. So that's cool. Yeah, that's pretty much it.